OK, so next thing, let's try computing the, use the computation graph to see how we can compute the gradient of the loss in one particular perceptron. One simple perceptron you have, you want to compute the gradient. OK? Let's see how does it look like. So first of all, just remember, we are just computing the gradient for one single sample point, right? This means that you might have so many images inside your data set with the corresponding labels. You just choose one of them at random, right? So that is one of them. So it's going to have n different pixels. You put it at the input of your perceptron. It's going to do the computation. It's going to give you one output, right? Maybe your label is 2. It's going to give you 1, right? Or something else, right? Now, the thing that you're going to do, you're going to compute the loss between this output and the true label that you have inside your data set. Now, this guy is definitely depending on all the weights and bias that you have inside this single perceptron, right? Meaning that if I change W1, then this Y is going to change, right? If I change the bias, the Y is going to change, and so on, right? So since that is going to happen, then I can compute the gradient with respect to all these weights, right? So I want to do that. Now, first thing, what are the variables here? Just look at it. What are the variables that we want to take the derivative with respect to them? Weights and the bias, right? So if I want to draw the computation graph, I'm going to do it like this, right? The first variable that are going inside this computation graph are the bias and weights, right? So if I change these guys, the output is going to change, right? So these are the variables, right? Now, how do I compute the output, which is the function I want to take the derivative with respect to? It means the loss. How do I compute the loss for a given set of weights and bias? How do I do that? Of course, I'm going to first compute z, right? I'm going to get all the x's, right? All the input, multiply them with the corresponding weights, add them to the bias. It's going to compute me the variable z, right? So z is a function of all those weights, right? So I first compute z. And how I compute it, I get the bias, I multiply it by 1. I get the first weight multiplied with the first input, and so on till the last one, right? So I do this computation. I add them up. This is going to compute me the variable z, right? Cool? OK. Next, after z, what do? I activate, right? So I'm going to pass this z over the activation function f. I'm going to get y, right? This y is computing me the output of the neural network, right? I want to compute the derivative of the loss, right? So what do I do next to this y? I compute the loss, right? So I'm going to get this y. I put it inside the loss function alongside with the true label. And this is going to give me the loss, right? So now I have the sample loss for a given set of weights, right? And this is the computation graph. Once I set the weights on the computer, this program is going to compute me the loss, right? Now I want to just write down how I can compute the gradient, right? So what do? The first thing that I should do is to just, I need to complete the forward pass, right? What does it mean? It means that I should just put the values like the, say I am in one particular iteration. I should just put the weights of that iteration here as the input. And this is going to compute me z, y, and the loss, right? These are now on your computer numbers, right? Maybe loss is 0.2. Maybe y is 4, right? Maybe z is, I don't know, 4.3, something like that, right? So these are numbers. Because you set the weights that you have in that iteration as the input, you computed everybody in between, right? Now that you have this one, you start to move backward, right? So you're going to say that I want to know what is the derivative of the loss with respect to y. Can I do that? Can I do that? If the loss is known, I can do this. Say, for instance, the loss is defined to be simply the squared error. So it means that I compute the loss, the r hat, I am computing it as y minus the true label v squared. Say this is my loss function, right? Now, if I want to compute the derivative of r hat with respect to y, what can I do? I can define another program which is computing 2y minus v, right? Everybody's clear? So when I have y, I give it to the forward program. It's going to compute me the loss, right? When I want to know the derivative, I put the same y. It's going to give me the derivative of r hat with respect to y, right? Everybody's cool now, right? So now, I can compute this one. I do have the loss function. This is the one which I have defined, right? And then I can compute this one. Now, what about the next thing? I do know what is the activation function, right? For instance, it's the ReLU function, right? So I can define the derivative of that ReLU function as well. So I would say if z goes inside the ReLU function, I'm going to get 0 for negative z. I'm going to get a linear function for positive z, right? Now, if I want to know the derivative, again, I'm going to say, when I have z, what's going to be the derivative of this function? Well, it's 0 when z is negative. It's going to be 1 when z is positive, right? So it's going to be a step function. Again, I can define this f dot alongside with f on my computer, right? And now, I do know what is the value of z, and then I can just compute this derivative as well, right? What about next step? So I want to get from z into every single weight that I have there, right? So I would say, OK, z is written as a linear function in terms of the weights, right? Let me just write you the term for z, and then just to make sure that you see it. So can you tell me what is z in terms of x and weights and the bias? It's going to be x1 times w1, right? Plus x2 times, and so on till xn wn, right? You have also a bias, right? Right? No, this bias is being multiplied with 1, right? Nothing, which we called it x0, right? So it's going to be x0 here, right? Now, if I want to know the derivative of z with respect to one of the weights, so it's a partial derivative of z with respect to one of the weights, say wi, what it would be? It's going to be xi, right? Right? Because if I'm talking about w1, then everybody else is constant, so x1 is going to be the derivative, right? So the derivative of z with respect to every single of those weights is the corresponding input, right? So I could say that derivative of z with respect to b is simply x0, which is 1. Derivative of z with respect to w1 is x1, and so on till the last guy, right? Now, if you want to compute the derivative of your loss with respect to b or any other weight, you would just move backward on this graph, right? So you would say, OK, this is going to be the derivative with respect to y, which I can compute by L dot, right? Then derivative of y with respect to z, which I can compute by F dot, right? Derivative of z with respect to any of the weights, the particular weight wn that I have, which is going to be the corresponding xn, right? Now, this guy, you can program it on your computer, right? Whereas writing down explicitly the gradient of the loss with respect to every single weight, even though in this particular case is possible, it's going to be more complicated, right? But now you can easily do it, right? Yes?
Since you know all the numbers in the whole
Yes.
so I don't think you have to go backward because the derivative of each one only relies on the input, not the output. So
You need to go, right? Because if I want to know what is z, I first need to move forward, right? I mean,
the first time you have to go forward. But
yes.
when you calculate the derivative, you already have all the values, so you can do any direction.
Oh, I see. Like you mean that this computation here is going to happen in one shot. Right, right. That is correct. I mean, you can think that you are moving backward. I got your point. You mean that when you want to compute this f dot, you don't need to first compute l dot. You mean that? That's right. That's right. Right. So you need to just build the computation graph. Once you have all the values, then yeah, you compute it in one shot. Yeah, that's right. Yeah. Questions? So everybody's cool? So you see how you can move backward in this neural network, right? This very simple network, right? So now, if you got this idea, now this is the time where we can start just making it a bit more complicated. So the whole idea, as I told you, is that you have this computation graph. Whatever operation you have on your computer is just going on this graph, right? And this graph contains variables on it, and then whenever you want to just compute the gradient, you need to just move backward on this guy, right? So you compute all the gradients backward, and then you just compute the product of them. This is going to be your gradient. Now, we can actually get rid of this kind of messy graph by just making things more compact, making them in a vectorized form. So let's say that I want to represent this whole output, this z1 to zn, in a form of a vector, right? Then I can write it down as a vector function, right? So it's a function g, which is taking x and computing all the values z1 to zn in one shot, right? So it's a vector function. It's a still a function, right? You give x to it, it's going to give you different z's, right? OK. That's your vector function. Now, you can compactly show this diagram in this form, right? You're starting from x. This guy is a scalar, right? Then you just go to z. This z is a vector, is a different kind of mathematical object, right? Then you get from z back to y, which is a scalar again, right? Everybody's clear? So when you move from one node to another, you can change the mathematical object, right? So x was a scalar, your function is computing a vector, right? That's no problem. Z is a vector, your next function is computing again a scalar, right? That's not a problem, right? You still can show it this way, right? But now, the question you might have is that, what if I want to move backward? I am happy with derivatives. What's going to happen here, right? Now, if we want to just look at the backward path, let me just start by defining this one to be the derivative. So if I have this vector function, I could say that the derivative of this vector function with respect to input is simply the derivative of everybody inside that, right? Everybody's cool? This is not a gradient. You see it, right? This is not a gradient, right? Don't confuse yourself. Z is not a function of multiple variables, right? Z is a function of a single variable x, right? Everybody sees that? So z is only function of x. Now derivative of z is derivative of its first term, second term, third term till the last one, right? You could have a vector input and a vector output. Then you need to have the gradient of the first term, gradient of the second term, till the gradient of the last term. This is what we call a Jacobian, and we're going to meet it pretty soon, okay? So no worries in that respect. But right now, you're not inside this vector. You're not computing partial derivatives. It's not going to change the computation graph, but I want to make it clear for you, right? So you have n different outputs. You have a single input. You need to know the derivative of every output with respect to every input. You have one input. You don't need to just search for inputs, right? Everybody's cool, right? OK. So I have this notation. This is the derivative of output with respect to input. And now, if I want to just get on the computation graph and show the backward path, what I can say? I have this particular y, right? And then I have this z. This is n-dimensional vector. If I want to compute the derivative of y with respect to input, what kind of derivative do I have? A gradient, right? Because y is a function of multiple things, then you have lots of partial derivatives, right? And then you can put them inside one vector. This is going to be your gradient vector, right? Now, again, you have this z, which is n-dimensional. You're getting back to x, which is a single dimensional. You have this vector derivative. What is the dimension of this guy? What is it? It's not 1, n, right? N is dimension of this guy. 1 is dimension of this guy, right? So it's going to be n to 1, right? Here you have again 1 to n, right? Everybody sees that, right? Clear? Now, the thing here is that when you are getting from y back to z, you have a derivative of the gradient form, right? When you get from z to x, again you have a derivative, which is of the vector form, right? And now I want to see whether I can write down the derivative of y with respect to x in a compact form. Okay. If z was simply a scalar, what would you do? Just product them, multiply them, right? So you're going to say here is f dot, g dot, just multiply them. That's going to be the end-to-end gradient, end-to-end derivative, right? So let's look at this case. What can I say? I can say I want to know the derivative of y with respect to x, right? So it's going to be derivative of y with respect to every single entry of z, right? Times derivative of z with respect to that entry of z with respect to x, right? What is this guy? Derivative of y with respect to one particular input. This is, does it exist inside the gradient? Yes or no? Inside this gradient, what do you have? Multiple entries, and those entries are partial derivatives, right? So it's going to be derivative of y with respect to z1, derivative of y with respect to z2, till derivative of y with respect to the last z, right? So what is this green guy then? This is entry n of the gradient, right? What about dz n with respect to dx? Look here. What is it? This is derivative. Can I show it in this g dot? This is, again, entry n of that g dot, right? So I can say that this is an inner product, right? An inner product of the gradient, this guy, times this vector derivative, right? You see it? Do you see it? Right? Now, yes? I'm going to say it. No worries. Yeah. I mean, at some point you don't really need it because computer is going to do it. But if you want to know how exactly you can guess the right product, I'm going to explain it. Okay? No worries. So everybody sees that? So what is happening here? I'm again computing the derivative, another derivative, but my derivatives are no more scalars, they are vectors, right? I end up just computing the inner product, right? Right? So the key point here is that when you have a vectorized computation graph, like your nodes are not simply scalars, but they are vectors, you can still do the same thing. The only difference is that you need to know what kind of product you need to do, right? So this means that if you want to just move backward on this, for example, particular computation graph, what you're going to say, okay, I got from y to z n-dimensional vector, right? I got from z to x n-dimensional vector, right? Now, I want to get from y to x. What is the derivative of y with respect to x? What kind of object is it? Is it a scalar? Is it a vector? Is it a matrix? What is it? It's a scalar, right? So if it's a scalar, you have two n-dimensional vectors. You want to multiply them in a way that it ends up with a scalar. What should you do? You should do the inner product, right? That's it, right? So you didn't need to do all of those calculations. You just could say that, okay, I have two different vectors of derivative. I want to combine them, multiply them in a way that I end up with a scalar derivative. What should I do? I just do inner product, right? Everybody's cool? You see that? So you can always, if you get confused on any computation graph, you can always open it up in terms of the scalars in that. You see how exactly it looks like. But at the end of the day, all the time, you're going to end up with one specific product of those different gradients, right? Yes?
So at this place, we call f, like delta f as gradient because it is a multivariate thing. And
Yes.
we calculate a lot of partial derivatives.
Yes.
So it's a gradient.
Yes.
And for g dot, we only call it as a vectorized derivative.
Derivative.
It is just taking derivative with respect to one, let's say like x.
Yes.
So that's why it's not a gradient, but
Yes, that's true. That's true. But at some point, you don't really distinguish between them anymore, right? I just wanted to make it clear for you how you compute g dot. But at the end of the day, you have one mathematical output, you have one mathematical input, and you want to know the derivative or gradient, whatever you want to say, of that output with respect to input, right? When it's multidimensional, when it's scalar, it's going to be a simple derivative. If it's multidimensional, scalar, it's going to be gradient. If it's a scalar, multidimensional, it's going to be a vectorized vector. If it's a multidimensional, it's going to be Jacobian, right? Yeah, these are different things. You define it in calculus, but computationally, all of them are the same thing, right? Are a derivative of one object with respect to another object, right? Yeah.
I was just afraid of, like, for example, in the midterm, we are given a, like a g dot.
No, you're not getting that. It's,
Whether it is a vectorized derivative.
no, it's not a calculus exam. So that one, no, you are not going to get such a question. Definitely, right? No worries. And at some point, we're getting rid of those specific products as well. We're going to just say one product, yeah, and we don't care. Because you get the idea that you can multiply any two things at some point, right? Yes?
Computationally, to do the derivatives, is there libraries to do it, or you have to see the whole thing yourself and do it analytically and then
No. Actually, this is what PyTorch does for you. Actually, PyTorch has been very successful for implementation of deep models simply because of the computation graph. So when you write down a function, if you say, I guess not today, but the next tutorial, he probably is going to take you over, like once you implement it by your own, once you use just the autocrat of PyTorch to just compare. But what is happening is that when you write down like x equal to, z equals to some function of x, then PyTorch in the background is going to make one x, and it's going to connect to z on the computation graph. It's going to build this huge computation graph for you. And when you say, like you see the last variable, and you say, OK, this y is the output, y dot backward. So you just apply method backward on that y. The thing that is going to happen, all of these backward gradients are there. So you're going to just one-shot compute all the gradient for you. OK? Yeah. So this is why it's successful, because it's going to make life much easier. Yeah. Right. The only thing that you care about is this particular gradient that you want, right? Because, for instance, x here, we're going to see, x is the parameter you want to update, right? Yes, I mean, here you don't have weights. It's just an abstract thing, right? I mean, in neural network, x is going to be the weights w, right? No. We're going to do it. No worries. We're not yet over with that. OK. Questions? Everybody's cool? So here, one point. X here is nothing, has nothing to do. Maybe it was a bad notation I've used here. X has nothing to do with the x inside your data set, right? It's just a variable, right? So you just think about a function, right? Right now, you don't think about the data set. We're going to get back there, and we just compute. You're going to hate me at some point that I do it, but no worries. I'm not going to leave it like, that's it, backpropagation is over. OK? So no worries about that. So now, so one thing that you can do, you can get this same idea that we had here, this idea of vectorized products. And you can apply it, for instance, on the simple single neuron that we just did the backpropagation on that. So what was the idea? we had this particular derivative here, we had another derivative here, and again we have one derivative here, right? So again, if you have y here, this guy is a scalar, right? Your loss is a scalar. Here you're going to have a scalar derivative, right? Z is a scalar, y is a scalar. This derivative is again going to be scalar, right? Now, but z here is a function of all these guys. What's going to be the derivative here? It's a gradient. It's a vector, right? Right? And what is the dimension of that vector? N plus 1, right? Exactly the number of inputs that you have. So you could say that, okay, let's say just this x is that dummy one and the original x that I had. And the weight vector that I have is the bias and all the weights. This is how we show it in the neural network, right? And then the thing that I can say that z that I'm computing is computed out of this x and w in this form, right? It's again a function of w. It's a scalar function of a vector. When you want to take the derivative, you have the gradient, right? And now you can compactly show it in this form. So this vector of weights, right, go through this function, which is changing one vector to one scalar. This scalar goes through another function, giving us a new scalar. Again, this guy goes through a loss function, giving us last scalar, which is the loss, right? And now I want to compute the gradient of that loss with respect to the weights, right? I want to do that, so I would say, okay, r hat is a scalar, y is a scalar. When I move backward, I'm going to have a scalar gradient, right? Y is a scalar, z is a scalar. If I move backward again, I'm going to have a scalar gradient. But if I get back from z to w, as you said, I have a vector. This is going to be scalar after the function operation. Now, if I move backward, I need a gradient, right? So I'm going to write down the gradient of z instead of simply the derivative of z, right? That's it. This is the only difference, right? And at some point, as I told you, like when you are over with this lecture, I hope that is going to be the case for you, that when you look at one variable, you don't think about this, what is that one? Is it a scalar, a vector, a matrix, a tensor, whatever that is? I can always compute a gradient, right? Wherever it comes from, it's going to have lots of derivative with respect to every single entry inside the other thing, right? And all of them can be collected in one big giant object, and that is the gradient, right? Okay, so that's it. So you're going to say that, okay, r to y derivative, y to z derivative, and z to w is going to be gradient. And again, the dimension is going to match, right? The dimension of derivative of r hat with respect to w should be n plus 1. And you see 1 times n plus 1. This is going to be n plus 1 dimension, right? So your chain rule at the end of the day going to end you up with one vector, which is exactly the gradient that you want, right? So now, just to make it compact, I guess that everybody sees it right now. But looking at this particular function, so the way that you write down z in terms of the inputs, so this is the way. So this w0 is essentially the bias. We just called it w0. And then when you want to compute the gradient of z with respect to this weight vector, you are going to compute the partial derivative with respect to every single guy. Oh, this is a typo again. This is wn, of course. I mean, this is just a typo, okay? And yeah, that is going to be exactly the x vector, right? This is going to be x vector. So this means that instead of this gradient, I simply put x here, right? And again, x is, for instance, your data sample. So it's not a hard thing to put it there, right? Now, if you want to compute the gradient, derivative of loss, derivative of activation times your data point, this is going to be your gradient, right? So yeah, that's just completion of the whole story, right? Derivative of loss, derivative of the activation, and finally, this is going to be your data point, right? Everybody's clear? Questions? So, moral of the story, whatever computational function that you have, whatever operation that you have, on your computer, you can think of it as a computation graph, right? And that computation graph, you don't really need to think about, again, scalar variables. You can think about giant variables, right? All of them collected in one capsule, one object, right? And these objects are connected through some operations to each other, right? As long as you know what is the derivative of every single operation on this graph, you can always move from the output towards the input, right? And this is exactly what's happening inside the neural network, right? So in the neural network, what you have your input, right, being connected to a bunch of weights, right? You can do exactly the same thing I did to the neuron, right? You can just think weights are here, input is the one which is computing the first layer, right? Again, for the second layer, you can do the same thing. Third layer, you can do the same thing towards the very end, right? And each time you want to compute the gradient of the output with respect to any set of weights, you just need to move backward on this computation graph till you get there, right? And then you multiply anything that you see in between. How you multiply them? You multiply them in a way that the dimension gonna match, right? And then finally, you're gonna have the gradient, right? And this is basically the way that your computer is doing the computation, right?